All right, so I go ahead and erase this. All right, sorry about that. So we're going to be doing some more complicated examples, and we're going to be finding this integral, okay? And finding the integral is more difficult than taking the derivative, because again, the derivative, we have our rules. We have the quotient rule and the product rule and the chain rule, and then all of the special rules for the logarithm and trig functions, stuff like that. And it's fairly straightforward. As long as we're good with our algebra, we know how to do it. But finding the integral for calculus is a little bit more difficult. Sometimes we have to get more clever, or we have to be more clever. So for instance, in this one, what can we do? Well, I see a copy of sine and I see two copies of cosine. All right, so I'm just thinking of antiderivatives. And I know with the trig functions, either when we take the derivative of trig functions, it's something squared, right? Like cotangent squared, or if we take the derivative of sine and cosine, it's, cosine or sine. And I guess instead of something squared, it's a single term. But here, we can break this up, okay? And I know that some of these trig functions, when we take the derivative, give us two terms. So that's my motivation. So I'm going to take that cosine squared and I'm going to break it up into a product. Cosine times cosine is cosine squared. All right, so I have to think a couple steps ahead because I'm just thinking of, antiderivatives and trig functions. And now what do we have? We have, this is sine over cosine is tangent. 1 over cosine is secant. All right, I can definitely write out tangent and secant, but it's a little bit more familiar to us when we see it like this, right? And we know that the antiderivative of secant tangent is the secant, because the derivative of the secant is secant tangent. So there you go. All right, so just a little example of how we're going to have to do these manipulations. All right, so let's see how you guys do. You guys are going to take find the indefinite integral. I'll give you guys 4. So there's 1. This one's tricky. Let's see how you guys do on number 2. And here's the 4th one. So after I write the 4th one out, go ahead and push pause. Try them out on your own and see how you do. All right. So let's look at number 1. So I am going to distribute the secant of t. And then when we do that, things look a little bit more familiar, right? Okay, so for instance, the antiderivative of secant squared is the tangent. And the antiderivative of secant tangent is secant. All right, and then for indefinite integrals, what's the last thing we need? We need the plus c, so make sure you don't forget that. Okay, and then remember, if you wanted to check, you can always take the derivative going the opposite direction. Okay, so derivative of tangent is secant squared. Derivative of secant is secant tangent. Derivative of a constant is 0. Okay, number 2. So same thing with number 2. I'm going to distribute the 2t, because I know how to take the antiderivative of an exponential function, but I don't know how to take the derivative of a product like that. Okay, and then just thought process. Again, I know how to take the antiderivative of 2 to the t, but again, this is a product, and I don't know how to take the derivative of a product. So what I'm going to do is I'm going to use a reverse exponent rule, and we have this rule that if we have something like ab to the x, we're allowed to distribute the exponents for products. So it's a to the x, b to the x. So in our case, we have 2 to the t, 5 to the t. The exponent's the same. So going backwards, we can multiply the bases and raise it to the power t. Okay, so this is going to become 2 times 5 to the t. All right, which becomes what? What's 2 times 5? 10 to the t. All right, so now we're ready to take the antiderivative. So the antiderivative of 2 to the t, if you remember, it's 2 to the t. Well, and again, we can always work backwards. Remember, the derivative of this, 2 to the t, is 2 to the t natural log of 2. But there's no natural log of 2 right here. That coefficient isn't there. So we're going to have to divide it out. And same thing here, 10 to the t, and then divide out that natural log of 10. Okay, what's the last thing we need? Plus c, because it's a family of functions, infinitely many functions. All right, so let's see what we have next. All right, so tangent squared, no antiderivative of tangent squared. So we have to think of our trig functions. Let's see, we see this square. So when I see square on tangent or cosine or sine or cotangent, I think Pythagorean theorem, right? A squared plus b squared equals c squared. So when we're doing that, when we're doing the cosine squared plus sine squared equals 1, and we're talking about tangent, that means we're going through and we're dividing everything by cosine squared. So tangent is related to secant squared, okay? So, and that's important because secant squared has an antiderivative. Secant squared has an antiderivative. All right, so let's transform tangent squared theta into secant squared theta. And we can do it 2 ways. We can make a substitution because tangent squared is equal to secant squared theta minus 1. And actually, let's just do that. I think that's the most straightforward. Okay, so let's do it. Okay, so we're saying then that tangent squared is secant squared theta minus 1. All right, and that was our strategy because there's an antiderivative to secant squared. Let's clean it up. 2 minus 1 is 1 plus secant squared theta d theta. All right, now let's take the antiderivative. So the antiderivative of 1 is theta plus tangent theta. And then what's the last thing we need? Plus c. And remember, you can always check your work by going in the opposite direction and taking the derivative with respect to theta in this case, okay? So we always have our checks and balances. Finally, number 4, notice the arguments are different in number 4. We have a 2x on top and an x on the bottom. Remember, we're not allowed to just cancel the x. We can't cancel things in the argument. Remember, you can think of this as like parentheses. It's behaving as a function. So nothing to cancel. So with trig functions, we have to use identities to change the argument. So for instance, sine of 2x, if we wanted to change that argument to x, we have to use an identity. And if you remember, sine of 2x is equal to 2 sine x cosine x. So let's make that substitution. All right, and then look at this lovely thing. We have a sine x that cancels, and then once we're able to cancel that sine x, our life gets a little bit easier. All right, we're just looking at 2 cosine x. If you want to, you might skip this step as well. You can do it in your head. But you can also move that constant out, so you can just focus on the antiderivative of cosine x. And the antiderivative of cosine x is sine. And then, of course, because it's an indefinite integral, you need that plus c. Okay, there you go. All right, so we're going to go back to definite integrals now. And the definite integrals we're going to be looking at are a little bit more difficult. Just so we can start seeing how integration is a little bit more challenging. So for now, let's evaluate the following definite integrals. So remember, because it's a definite integral, we're no longer going to have a family of functions. We're going to end up with, a constant. We're going to end up with an area because it's a definite integral. And we know it's a definite integral because we have these limits of integration. All right, so 0 to pi over 4, that's telling us to evaluate an area. All right, so again, let me write these out. I have 3 this time. After I read out all 3, go ahead and push pause. See how you do with the more challenging ones, and then come back and we'll review our solutions. All right, so there you go. Push pause, and then we'll see how you guys do. Okay, so let's see how we're doing on these definite integrals. So I'm looking at number 1, and I see the cosine squared, okay? So I'm always thinking, oh, that's the Pythagorean, right? So something like 1 minus cosine squared, something like that. But we do not have that. We have 1 plus cosine squared. So that's a little bit different. So my strategy is going to be different. I'm not going to be using the Pythagorean theorem. So what I can do instead, and let me just tell you why. If we were to make that substitution, right, 1 minus sine squared, we would just get 2 minus sine squared on the top. And we haven't gotten anywhere. That still doesn't help us. So I see that there's 2 terms in the numerator. So I'm going to separate out the fraction. So for number 1, I'm going to do the first term divided by the denominator plus the second term divided by the denominator. Okay, so now we're kind of making progress. All right, so for instance, this first one is going to become secant squared. And again, we know we can take the antiderivative of that. And then the next one simplifies to 1. All right, d theta. So we can take the antiderivative. Antiderivative of secant squared, that integration is going to be tangent theta. Integration of 1 is theta. And we're going to evaluate from 0 to pi over 4. Okay, so let's see what we get. So tan of pi over 4 plus pi over 4 minus tangent of 0 plus 0. Okay, so tangent of pi over 4 is 1 plus pi over 4. And now tangent of theta is 0 plus 0 is 0. So we can't do anything. So we'll just leave it like this. 1 plus pi over 4. Okay, so the next one is a little bit different because normally we have the dr over here, right? And this time it's in the numerator. Well, we're allowed to move it outside, right? Because that's how multiplying by fractions work. So for number 2, to just see it a little bit better, you're more than welcome to add this additional step by just separating out that integram. All right. And then the antiderivative of this, when we take that integral, that's the inverse sine. And now we're going to evaluate it from 0 to root 3 over 2. Okay? So inverse sine of the upper limit of integration minus the inverse sine of the lower limit. And remember, with inverse sine, we're going from negative pi over 2 to pi over 2. Okay? So those are where our solutions have to lie. Okay? So for instance, root 3 over 2, that would land us in the first quadrant. And since sine of pi over 3 is root 3 over 2, the inverse sine is going to be pi over 3. All right, and then what's the inverse sine of 0 in this interval? It's right here, minus 0. All right, so we're looking at pi over 3. All right. And again, definite integrals have a constant. It's defining an area. So let's look at this last one. And again, I don't know how to take antiderivatives or integrals of quotients. Okay, so what I'm going to do instead is I'm going to expand this. I'm going to do x minus 1 cubed. Okay, so again, you can do it 2 ways. You can do, x minus 1 times x minus 1 times x minus 1. There was also a theorem in pre-calc using Pascal's triangle, right, where the coefficients of cubing something were 1, 3, 3, 1. And then I'll just write it out. I love this little theorem. So this would be for a plus b cubed. And your coefficients, according to Pascal's triangle, are 1, 3, 3, 1. And we start with the first term. And it's the third power. And then it just goes down from there. So 3, 2, 1, 0. And then the second term, b, does the opposite. So 0, 1, 2, 3. All right, and then I just do plus. And then if b is negative, then those signs are different. Okay, so in our case, a is x, b is negative 1. So we're looking at x cubed plus 3x squared, b is negative 1, plus 3x negative 1 squared plus negative 1 cubed. Okay, so it's a fun way to expand your binomials. I don't know if you guys remember that from pre-calc. But there you go. Okay, so let's write that in. I love little reviews like that, especially interesting ones. I really like Pascal's triangle. Why are we doing that, right? Sometimes we get so lost in the process we forget what we're doing. Okay, so we just said Pascal's triangle gives us this. Do you guys know how to derive Pascal's triangle? You start with a 1. Do it like this. Start with a 1. And then it's a triangle, so it goes 1 entry, then 2 entries, 3, 4, 5. And how you determine the next entries is you add up what comes, to the right and to the left. So 0 plus 1 is 1. 1 plus 0 is 1. Okay, and now the second row, 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 0 is 1. etc., etc. So 1 plus 0, 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 0 is 1. All right, and if we wanted to take binomial to the fourth, we would use this row. Okay, there you go. So now what I'm going to do is I'm going to break up this numerator by dividing each term by the denominator. Okay, and then we can clean it up. So we're going to be looking at x minus 3 plus 1 over x minus, I'm going to think of this as x to the negative 2, just to help with my integration. Okay, so now we're ready to integrate because we know how to take the integral of all of these little parts. So the integral of x is 1/2 x squared. Minus 3 is going to become minus 3x. Remember what the integral of 1 over x is? Oh, I lost the 3. Sorry. It's, well, the 3 is right here. And then the integral of 1 over x is the natural log of, should be absolute value of x. And then, but it doesn't really matter because our interval is from 1 to 2, right? And then finally here, our new exponent is going to be negative 1. And then it will be minus negative 1 times this. So minus minus becomes plus. And we're going to evaluate that from 1 to 2. Gosh, this is a long problem, right? Well, I guess it's long if you also talk about Pascal's triangle and expanding binomials. All right, let's plug in the upper limit of integration. Okay. And now we're going to plug in the lower limit and subtract. So 1/2 minus 3 plus 3 natural log of 1, which is going to be 0, plus inverse of 1 is just 1. All right, so what do we get? This is going to be 4 divided by 2. I'm going to switch colors. It's 2 minus 6. Natural log of 2, I don't know what that is. So I'm just going to leave it. And I don't need absolute value around the 2 because it's positive. All right, plus 1/2. And then minus 1/2, minus 3, minus natural log of 1 is 0. So we'll just exclude that. And then minus 1. Okay, so what happens? 1/2 minus 1/2 cancels. And then we have 2 minus 6 is negative 4. Minus 3 is negative 7. Minus 1 is negative 8. And then plus 3 natural log of 2. I'm going to pause because I think there's a mistake somewhere. So let me see if I can find it. So what happened? Plus 1 over x. Okay, so 1/2 2 squared minus 3 plus 1/2 minus 1/2. Okay, did I make a mistake, guys? 4 divided by 2 is 2 minus 6 plus 1/2 minus 1/2. Oh, there it is. Minus minus becomes plus. Whew. Is that the only one? All right, let's try this again. 2 minus 4 is negative 4. Plus 3 is negative 1. Minus 1 is negative 2. There you go. All right. And again, that's a constant, and it's defining an area under the region.